Today I want to tell you about Bayes' rule for densities, which is, much like Bayes' rule for probabilities, a way of going from the density of one variable conditioned on the value of a second to the density of the second conditioned on the value of the first. As always, let's start with a story. Alchemy is tricky under the best of conditions. The alchemist had developed a new recipe, but the same recipe, even when followed to the best of the alchemist's ability, did not always result in a potent potion. The alchemist decided to call the probability that a potion worked P, and originally, because of a lack of information, modeled P as being uniform over the interval from 0 to 1. The alchemist then ran an experiment, making 6 of the potions from the new recipe, and trying each in turn. Given the result that there were 2 successes and 4 failures, what is the new distribution of P given this information? Recall that the probability a random variable W falls into a differential interval dW is the probability W is in dW equals the density of W at little w dW. Here dW stands for both the differential interval and the length of the interval. The function f sub w of W is the density of the random variable W. Alternatively, the density can be viewed as a type of derivative. The probability that W falls in the differential element W divided by the width of that element dW equals the density of big W at little w. Conditioning on information about differential intervals is a bit different. Suppose that one is given the information that y is in the differential element around y. That says that the random variable y is arbitrarily close to little y. Hence, from a conditioning point of view, this is the same information as if big Y equaled little y. Consider using this idea with Bayes' rule. If differentials could be canceled just like regular variables, then the regular Bayes rule tells us that the density of x conditioned on big Y equaling little y evaluated at x times dx is the probability that x falls in the differential element around x, conditioned on y falling in the differential element around y. Applying Bayes' rule then tells us that that's the probability y falls in a differential element around y, given x falls in a differential element around x, times the probability x is in the differential element around x, divided by the probability that y is in the differential element around y. So this is just the density of y conditioned on big X equaling little x at y dy times the density of x at x dx divided by the density of y at y dy. Now the dy's cancel out, and dividing both sides by dx tells us that the density of x conditioned on y equaling little y at x is the density of y conditioned on big X equaling little x at y times the density of big X at little x divided by the density of big Y at little y. Note that the density of y given x equals little x at y and the density of x at little x depends on x, while the density of y at little y does not. That means that the normalizing constant, which is the density of big Y at little y, can be found by integrating the other terms. This gives Bayes' rule for densities. Suppose that x and y are real valued random variables with density f sub x and f sub y respectively. Let y be a number such that the density of y at little y is greater than 0. Then the density of x conditioned on big Y equaling little y at x will be the density of y conditioned on big X equaling little x at y times the density of big X at little x, all divided by that numerator where x has been replaced with w and we're integrating over all possible values of w. The density of x is called the prior density, while the density of the random variable x, given the condition that big Y equals little y, is called the posterior density. Note that the denominator on the right-hand side only depends on y after w is integrated out, and y is a constant on the left-hand side of the equation. So another way to write Bayes' rule for densities is as a proportion, using the proportionality symbol to hide the constant of proportionality. Some examples. 3x squared is proportional to x squared. X squared is proportional to 3x squared. 6 square roots of x is proportional to just the square root of x. For Bayes' rule, the following holds. For random variables x and y with densities f sub x and f sub y respectively, and little y a number such that the density of big Y at little y is greater than 0, it holds that the density of x conditioned on big Y equaling little y at x is proportional to the density of y given big X equals little x at y times the prior density of big X at little x. In words, the posterior density of x conditioned on y is proportional to the prior density of x times the density of y conditioned on x. With this equation, you can then find the constant of proportionality by dividing by the integral of the unnormalized density. In the alchemist story, p is a random variable that is uniform over the interval from 0 to 1. Hence it has density f sub p at a is the indicator that a is in the interval from 0 to 1. Let n denote the number of successful experiments for the 10 trials. Then the goal is to find the density of p conditioned on capital N equaling 4 at a, which is proportional to the density of n conditioned on p equals a at 4 times the density of little p at a. Here, the random variable n conditioned on p is a binomial with parameters 10 and p. So the density of capital N given p equals little a at 4 is 10 choose 4 times a to the 4th power times 1 minus a to the 10 minus 4 power. The 10 choose 4 is just a constant, so this is proportional to a to the 4th times 1 minus a to the 6th. Multiplying by the prior density of p at a tells us that the density of capital N given p equals a at 4 times the prior density of p at a is proportional to a to the 4th times 1 minus a to the 6th times the indicator that a falls between 0 and 1. This is an unnormalized density. To normalize it, we have to integrate the unnormalized density for all values of a. The indicator can be used to change the limits to 0 and 1, and the result is 1 over 2,310. That last calculation comes from a neat little fact. If I and j are integers, the integral from 0 to 1 of x to the I times 1 minus x to the j is I factorial times j factorial over I plus j plus 1 factorial. Dividing by 1 over 2,310 is the same as multiplying by 2,310. So that makes the posterior density 2,310 times a to the 4th times 1 minus a to the 6th times the indicator that a falls between 0 and 1. Now, this type of density that shows up in the posterior is called the beta distribution. Suppose that x has density which is proportional to x to the a minus 1 power times 1 minus x to the b minus 1 power times the indicator that x falls between 0 and 1, where a and b are greater than 0. Then we say that x has the beta distribution with parameters a and b. Now, like with the gamma distribution, it is customary to write out the English word beta for the Greek letter beta when talking about the distribution. The Greek letter beta, or at least the capitalized version, which looks like a capital Roman letter b, is used for the function that gives the normalizing constant for the density. When a equals b equals 1, the beta distribution is the same as a standard uniform over 0 to 1. So the beta can be thought of as a generalization of the standard uniform distribution. The normalizing constant of the beta distribution is called the beta function, and it's denoted by a capital Greek letter beta. So capital beta of little a and b is the integral from 0 to 1 of x to the a minus 1 times 1 minus x to the b minus 1. There is a simple relationship between the beta function, the normalizing constant for the beta distribution, and the gamma function, the normalizing constant for the gamma distribution. For a and b greater than 0, capital beta of a and b is equal to capital gamma of a times capital gamma of b divided by capital gamma of a plus b. So that's Bayes' rule for densities. That allows us to find the posterior density of a random variable given the prior and some extra random variable knowledge. See you next time.